Last time we have seen the different equations of turning, and now we will determine the relations to give us power and energy relationships in machine. So a machining operation will require, of course, power. The cutting force in a production machining operation might exceed 1000 Newton, and it is a high force. This is why we will have high power. So typical cutting speeds are several hundred meters per minute. So the product, to get the power, you should multiply the cutting force by the velocity. In case your force is in Newton and your velocity is in meter per second, then you will get your power in watt. Okay, so this is if you are working in SI units. Now you can work also in English units. In English units, then you will take, instead of having watt, your unit will be FT times LB over minute. In this case, the cutting force should be expressed in lb, and the cutting speed should be expressed in feet per minute. And also a unit that is widely used in English system is horsepower. So the horsepower will be obtained by dividing the power in feet lb per minute by 33,000. So in case they ask you in the exam to get the horsepower, then you should pay attention to first get your value in lb feet per minute, then divide by 33,000. Now, concerning the gross power, what do we mean by the gross power? You know that any operation will have losses, okay? So the cutting power will be your output, but to provide this power, you will have some mechanical, due to mechanical losses, you should provide a higher power. Okay, so the gross power required to operate the machine tool will always be greater than the power delivered to the cutting process because of the mechanical losses in the motor and drivetrain in the machine. This is why, to account for these losses, you can define the mechanical efficiency of the machine, and then the gross power can be obtained as the cutting power over the efficiency. And in general, the efficiencies are relatively high. So the typical values of efficiencies for machine tools are around 90%. Now, sometimes also they can ask you to find the power per unit of volume rate of metal cut. So all you have to do in this case to get the unit power, it's called also unit power, is to divide the cutting power by the removal rate. And for the removal rate calculation, we have seen last time how to find it. So in case it's a turning operation, then you should have V times the F, okay, where F represents the feed, okay, and times D, which is the depth of the cut. So also, an important parameter is the specific energy. Okay, so we can say that the specific energy U is the unit power is given by PC over the removal rate. And in general, the specific energy will be given by a table depending on the type of operation, okay, and the material used. So here we will see together a table that we will use in problems. So here, for example, you have, depending on the material you are using, the value of the specific energy will change. Okay, so let's say we have a turning operation, and I am telling you that the material used is carbon steel with a hardness of 180. So you go to this table, you try to select to see where is your sorry, the screen stopped to share once. Okay, so we should go to the table. We try to select the corresponding value. So it's 180 is between a Brennan hardness of 180 is in this range. So I will select the specific energy equal to 1.6 Newton meter per millimeter cube. Or if I'm working in English units, I will select this value. Okay. Now pay attention for something. You have a certain condition here. They told you that the values of unit horsepower and specific energy in this table for different materials is based on a ship thickness before cut equal to 0.25 millimeter. So if you have a different chip thickness, you cannot use immediately the values here. You will see what we should do. So in case T0 is different than 0.25, we will see that we can obtain the values by the use of a correction factor. What do we mean by the correction factor? We have this graph that will tell us that for different thicknesses, so if you have chip thickness different than 0.25, then you should multiply the U value you got from the table by the correction factor. And you can see in this graph that for 0.25, the correction factor will just be 1 because you can take the values as they are from the table. On the other hand, for example, if you have a chip thickness before cut of 0.5, then you say that I should go to this graph to determine the correction factor. Let's say here in my graph, it's nearly 0.85, for example, in case you have T0 equals 0.5. So what you do, you say the correction factor is 0.85. So when I go to the table, let's say I told you I am using cast iron of hardness 150. So you go to the table, you say I should select my variable, my material is in this range. So I will take for you for the value of my specific energy, I will take 1.1, but I should multiply this value because the thickness is different than 0.25. So for example, for thickness of 0.5, I should multiply it by 0.85. And in this way, I did the required correction, okay? So chip thickness before the cut also affects the specific energy and unit horsepower. So as T0 is reduced, the unit power requirement will increase. Therefore, we have a relationship between the size of the cut and the correction factor. So as you can see here, the results were summarized in this graph. So for example, in grinding in which the chips are extremely small by comparison to most other machining operations, we have in grinding the required energy values are very high. So the U and the values of internal energy will be, I should take into consideration that they should be increased. This is why I should make a certain correction. So I should multiply the value I get from the table by the correction factor. And if T0 is smaller than 0.25, then the operation will require more work because it's more accurate operation. So I will have a correction factor larger than 1 below 0.25, while if the thickness is larger than 0.25, then the correction factor will be smaller than 1. Okay. Now, concerning the increase in temperature during the operation, we have several analytical methods are used to calculate the cutting temperature. And one of these techniques is the method developed by Cook, which was derived using experimental data for a variety of work materials to establish parameter values for the resulting equation. So this is an empirical equation obtained experimentally. And this equation will predict the increase in temperature at the tool chip interface during machining. You know that because of friction and contact between the two, then we will have, during cutting operation, we will have increase in the temperature at the interface. And this increase in temperature delta T can be calculated function of the internal energy U, specific energy U, the value of the cutting speed V, the chip thickness, and the volumetric specific heat of the working material. Volumetric specific heat is rho times C. And also function of the thermal diffusivity of the work material. So you can see that higher is the diffusivity, it is expected that delta T will be reduced. And also higher is the volumetric specific heat, also delta T will be reduced. Because you know that in general, if the diffusivity coefficient is high, this will help into evacuation of heat. And also for the sensible heat Q, it's in general, it's equal in general when we calculate it. If you remember before, we did m dot Cp delta T. So if the density increase and if the specific heat increase, delta T will be reduced for the same amount of heat. This is why when rho C increase, delta T will be reduced. While when the specific energy in the operation will increase, this means that we are the heat that is given to the system is higher, so delta T will be also higher. So this is how we can calculate the value of delta T during the operation. So these were the main equations for chapter 17. We will start to do problems on this chapter. So already the equations and problems are posted in problem section. So you can see for each chapter what are the main equations. Plus that before the solution of problems, we have a summary of the main equation used. So these are the main equation used in these chapters. So we have introduced together the removal rate in turning operation, the chip thickness ratio, how to calculate the shear plane angle. Phi is the shear plane angle. It can be calculated function of the rake angle alpha and the chip thickness ratio R, which is T0 over Tc, using the following relation. So in case you have the thickness ratio and the rake angle, you can deduce the value of phi. Sometimes maybe they can give you phi, you can deduce alpha, etc. So you can play with these relations. Now for the shear strain during the process, you can calculate it as function of the two angles characterizing the operation of the shear operation, which are the shear plane angle and the rake angle. And the merchant equation will give you the optimal value of phi, okay, which will minimize energy in the operation. Also, all of these relations, you can see their derivation in the YouTube links I posted for you. And we derived the majority of them together in the course material last time. Now, concerning the coefficient friction, we have seen that it will be given as the ratio of the friction over the normal, and the friction coefficient will give us the angle beta, which represents the angle between the resultant, okay, because you know that if you represent your force, so this is F, this is N, okay, you will get a resultant force. So this is F, this is N, let's say. The resultant reaction, the resultant force, if you want to determine what will be its angle with the normal, so if you want to determine beta here, all you have to do is F over N. Okay, so you can determine the direction of the resultant using the friction coefficient. So tangent beta is equal to mu. Now, concerning the shear plane stress, it can be calculated as the shear force over the area of shear. And we have seen together that the area of shear can be computed as T0 omega over sine phi, where phi is the shear plane angle. Now, when we have machining operations, we have seen how to relate the forces. So if you remember, we derived these relations together last time. And we said that depending on the forces we know, we can deduce the others. Please, sometimes whole summaries, they will not include all formulas. And this is why also check الايكويشنز تبع chapter 17 لانه بالايكويشن تبع chapter 17 كمان حطيت لكم how to get directly cutting will thrust force function of the other forces. Okay, بس انه هون it's a small summary of all equations. And concerning the power, today we have derived the following relations together concerning the power, the horsepower in different units. يعني مثلا هون لازم تعرفوا انه here the units used here should be English unit for FC times V لأنه when you divide by 33,000 you will obtain the unit horsepower. مفروض FC and V يكونوا in English units. So please pay attention for units. You know that units are very important in this course. And finally, for the cutting temperature, we have seen the empirical relation together. The remaining relations in chapter 18, we will introduce them when we finish problems of chapter 17. Okay. So let us start by doing some application problems. So in an orthogonal cutting operation, the rake angle is given. So rake angle is alpha. So So you have the value of alpha. The chip thickness before the cut, this is T0, it is 0.3. And the resulting chip thickness after the cut is 0.7. So this is TC. They are asking for the shear plane angle phi and the shear strain for the operation gamma. So always go back to your equation. I need the phi and gamma. So if I go back to my equations, the shear plane angle is given by the following expression. In the given, they gave me T0 and TC. So the first step will be to calculate the chip thickness ratio. Then I substitute R in by its value, and the rake angle is 12 degrees. So I have everything. I can calculate the angle phi by doing tangent -1 of the result. Now, concerning the shear strain, once I find phi, and alpha is already given, I replace phi obtained from this equation here. I can get then the value of the shear strain. So here it is just a simple, straightforward application of the formula. So as we said, first we use the formula of R to get R, then we replace in the shear angle formula to get phi, and finally in part C to get the value of the shear strain. So here maybe it's missing. So all I have to do is to replace in the expression of shear strain, and I get a gamma. Another problem, the cutting force and thrust force in an orthogonal cutting operation are given. So here I know the thrust force and the cutting force. So this is Fc, and this is Ft. They gave us also the rake angle. So alpha is given. This is alpha. The width of the cut W is given by 5 millimeter. The chip thickness just before the cut is 0.6. So this is T0. And the chip thickness ratio R is given. So R represents the ratio of T0 over Tc. Since I know the value of T0 and I know the ratio, I can get the value of Tc. The question is to determine the shear strength of the work material and the coefficient of friction for the operation. You know that the shear strength is calculated based on the shear force over the shear area. Okay? So my purpose here, in order to calculate the shear strength, I should find first what is Fs and what is the area of shear. Now, for the area of shear, it is given by T0 times omega, which is the width of the material, over sine of phi. So the first step here is to get the angle phi. Already the thickness is given. T0 is 0.6. The width of the cut is 5. I know it also. Still, I need to get phi. To get phi, I need, it's a function of the ratio R and the rake angle alpha. The rake angle alpha is given, it's here. And also the thickness ratio is directly given. So I can calculate AS, no problem for AS. Now, concerning the shear force, I want to use the formula of the shear force Fs function of the cutting and thrust force. So if I go back to my formula sheet, I have the expression of Fs directly function of Fc and Ft. So from this formula sheet here, I can find the expression of Fs function of Fc Ft. So all I need is the angle phi. The angle phi is already calculated in the previous step. So I replace the cutting and thrust force by their equation to get the value of the shear force. Okay, so this is what I will do here. So by applying the formula in the formula sheet, and of course, first I get phi. I get phi from the rake angle and the ratio R. I get phi, I replace back into the expression of Fs. I can find then the value of Fs. And for the area, as I told you, it's omega T0 over sine phi. I get it. This will allow me to calculate the shear strength. Now just pay attention for units. Since the force you got, yani the thrust and cutting force are both in Newton. Since they are in Newton, then your result for Fs will be in Newton. And since the area is in millimeters square, because the dimensions T and omega, T0 and omega are in millimeter, then your shear will be Newton over millimeter square or megapascal. Okay, so this is how I calculate the shear strength. Okay, and now if I go back to the questions, they also need me to determine what is the coefficient of friction in the operation. To determine the coefficient of friction in the operation mu, this is my purpose. To get the mu, I need to find F and N, because mu is F over N. Okay, so to calculate mu, I should go back to my formulas to calculate F and N. I have here F and N. These are the expressions function of the cutting and the thrust force, so I can calculate them, and this will allow me to find the value of mu. Okay. Also, in case if you want, if they tell you a second method to get mu, if they tell you that the operation is optimal, then you can get the value of beta from the Merchant equation. So in case we have an optimal cutting operation, then it will satisfy the relation of Merchant, which is phi equal 45 plus alpha over 2 minus beta over 2. So if you rearrange your terms, you know alpha, you calculated phi, then you can calculate beta. And from beta, you will calculate the value of mu. But pay attention, the condition is that the angle used is the optimal one. So to verify this, here they should be clear in the question. If they tell you that it was the angle phi was selected as optimal, then you can use directly this equation. And to verify this now, you can check by calculating F and N and setting mu equal to F over N. And then since you can get beta as tangent minus 1 of mu, so you can verify if the cutting operation was optimal or not. Okay. Now, another problem, low carbon steel having a tensile strength of 300 megapascal and a shear strength of 220 megapascal is turned at a cutting speed of 2.5 meter per second. So here we have a turning operation. The type of material used is a low carbon steel. The tensile strength is 300 megapascal and the shear strength is 220 megapascal. And the cutting speed in the turning operation is 2.5. So this is the value of B. We have the feed is 0.2 millimeter per revolution. So this is F. We have that the depth of the cut is D. And the rake angle is given. And the ratio, chip ratio is also given. Using the orthogonal model to approximate turning, determine the cutting force and the feed force. So we want to determine FC and FT. Okay. So now the first step is to find the angles that are not given. And here we don't know the shear angle. The first step is to get the shear angle. Okay. So since we know the rake angle and we know the chip ratio, so first step to do, we get the value of shear angle. Now, once we have the value of shear angle, we can calculate the area of shear, which is determined as T0. Now, by analogy here, okay, because we are using the orthogonal model, we know that in turning operation, the equivalent to W is the depth, D, and the equivalent to T0 is the feed, F. So we will do F times D here. Okay. And concerning Phi we already calculated in the previous step, so we can calculate then the value of the area. Okay, so here in general the feed is given per revolution, but since we are just calculating a rate يعني per second, then we will take the value of T0 in millimeter, the value of F in millimeter. So it's 0.2 millimeter times 3 millimeter over sine of 25. The answer will be in millimeter square. Once we got AS and knowing the value of shear strength, we can calculate the shear force, FS. So now FS is AS, which is the shear area times the shear strength. This is why they gave us the shear strength in this problem. So we replace, this is the shear strength as we replace it. Since it is provided in megapascal and the unit of the area is millimeter square, so millimeter square times megapascal will give us the shear force in Newton. Now, in order to calculate the angle beta, يعني in general, okay, in general, the cutting operation are always optimized. Okay, so you can use the Merchant equation in your problems. So from Merchant equation, if I know the value of alpha and I know the value of the rake angle and the shear angle, I can deduce the value of beta. Okay, so I can get that beta is 45 degrees. And now, once I know the value, if you remember in chapter 17 equation, هلا هون مش محطوطين هول التو equations بالفورمولا شيت اول شيء، بس عندكم اياهم here in the equations here. You can see them. I will go back. We have seen them last time. So if you remember, after writing these relations, we said that by just using the set of equations we derived, okay, we can find the cutting force and the thrust force function of the shear force and the angles beta, alpha, and phi. So it depends on what are your unknowns, you select your equations. I mean, in the previous problem, you know when you know the cutting and the thrust force, you can determine all other forces. Okay. Now, if you just know the shear force and beta, alpha, or phi, you can determine the cutting force and the thrust force. Okay. So just by using the combination of previous equations, you can get these two. So when the cutting and thrust are unknown, then you can use these two formulas to get the cutting and thrust force. All you have to know is the shear force and the angles. Okay, this is why here, before writing these expressions, we got the values of shear force and the values of the different angles. So after calculating the different angles and the shear force, all we have to do is to replace back in the equation for FC and FT, and this will give us FC and FT in Newton because FS is in Newton. Any question on this? Another problem. In a turning operation on stainless steel, the cutting speed is 150 meter per minute. The feed is 0.25 millimeter per revolution, and the depth of cut is 7.5 millimeter. How much power will the lathe draw in performing this operation if its mechanical efficiency is 90%? Use the table 17.2 to obtain the appropriate specific energy value. So in this problem, we have the value of V, the cutting speed is given. We have the feed, F, and the depth, so we can calculate the removal rate easily. And we need to determine how much power is needed for this operation, knowing that the efficiency is 90%. Okay, so as a first step, okay, we know that to calculate the removal rate is V times F times D. Just also pay attention for units. So here, V is provided in meter per minute. Since I am working with F and D in millimeter, so I have F provided in millimeter and D provided in millimeter. So I will convert V from meter per minute to millimeter per second, because the unit time used in general is second. So to convert 150 meter per minute to millimeter per second, I should multiply by 10 to the power 3, and I should divide by 60 to go from minute to second. Okay. Now, once I obtain the removal rate in millimeter cube per second, in order to obtain the power, so the question was to obtain the power required for the cut. So first, I get the cutting power. Then to get the gross power, I divide by the efficiency. So the gross power is the cutting power over the efficiency. So the first step, in order to get the gross power, I should calculate the cutting power. The cutting power can be calculated as the removal rate, which I calculated already, times U. So now, to get the specific energy U, what I should do is I should use my table. Okay. Now, I should check the type of material used. They told me that the turning operation is performed on stainless steel. And concerning the value of T0, we said that T0 should be, if I want to use the table without correction, T0 should be equal to 0.25. And the analogy between the orthogonal model and the turning operation is that by analogy, T0 in the turning operation is represented by the feed. So since the feed is 0.25 millimeter, then I don't have to do any correction. So I can take the value as it is from the table. Okay. So now I will check for stainless steel. Here, in general, they should also give you the hardness. But already يعني ما في غير value واحدة بالتable للstainless steel. So since I'm working in SI units, I will select the value in Newton meter per millimeter cube, which is 2.8. So now I can just say that U is 2.8 joule per millimeter cube. So if you just pay attention, since U is joule per millimeter cube, if you want to obtain your power in watts, the removal rate should be provided in millimeter cube per second. Because in this way, millimeter cube will cancel, will be simplified, and you will end up with the unit joule per second, which is watt. Okay? So the cutting power you obtain will be in watt. You can then find, by dividing by 1000, you can get it in kilowatt. And since they want the gross power, the last step will be, so here I will add it for you. Okay. So here, when they ask for the power of the machine, this means the gross power. Okay. So the last step, يمكن it's missing here, you should add it. So the last step to do is that the gross power is calculated as the cutting power over the efficiency. So I should divide, if I want to have my value in kilowatt, so it's 13.125 over 0.9 kilowatt. Okay, this is the value of the gross power. Any question on this? So you have for chapter 17, you have 2 sets of problems. This is part 1. We will continue with part 2. So I will open a new session to continue with part 2. Okay.